This is AP Calculus AB Worksheet 1-9 for the Intermediate Value Theorem, Extreme Value Theorem, and Mean Value Theorem, AP Exam Word Problems. Oh my God, that was a lot to say. All right, so we were talking about all those theorems. Let's underline keywords. We have the word continuous. We have the word closed. We do not have the word differentiable. So anything that's talking about F prime of C, cross those off. It cannot be D. It cannot be E. We don't have differentiability. All right, so we're limited to A, B, and C. What are those things saying? All right, so literally all of those are almost the exact same thing. The one difference being there's closed interval there. It doesn't really matter. Ignore all of that stuff. Pay attention over here. This is saying the height at some point is 0. Okay, well, if it's talking about height, it's talking about intermediate value theorem, which we have permission to use because it's continuous. But the problem is to talk about an actual height, you need to set up some sort of rectangle for intermediate value theorem, and we don't have any points, so it can't be A. All right, what about B? This is saying that f of A is and f of B, there has to be some point in between, some height. The height at some point needs to be between the height of A and the height of B. Seems okay. Okay, let's talk about C. F of C is greater than or equal to f of x. Oh, wait a sec. I remember you. This is saying that the height at some point is greater than or equal to the height at all points. This, by definition, is a maximum. This is saying there is a maximum. Well, that one's clearly true because we have extreme value theorem, which we're allowed to use because we have closed and continuous. This is literally extreme value theorem, or at least one half of it. If it talked about maximum and minimum, it would be in the entire extreme value theorem, which means B was somehow false. And I knew why, but I wanted to come back and say, well, why? I can draw a counterexample right now. I can draw a continuous function that's closed, and this will not be true. It's plain devil's advocate, and here I go. What if I draw a graph? My graph is very lame, and it's just a flat line. It's just a constant function. Okay, well, I'm going to say that that height here, by the way, is 1. So the height at this point is 1. The height at this point is 1. So we need to find a height that is greater than 1 and also less than 1, and it can't be equal to. That's the main thing. This is missing an equal to sign. So is there some point in between here that has a height that is greater than 1 and less than 1 at the same time? And the answer is no, because we forgot the equal to sign. If it had an equal to sign, you could have circled part or letter B. All right. Number 2. We've got, keywords. Let's underline some things. I got the word continuous. I've got the word differentiable. If we had the word differentiable, we wouldn't even need the word continuous because differentiable implies that it's continuous. And we have the word closed. Look at that. With all 3 of these words, we have guaranteed all 3 theorems. All right, so, and this is the keyword, which of the following statements must be true? All right, it says, the minimum value is 12. Okay, I've told you this over and over, and I'm going to tell you again. If you ever have anything that claims, I know what the minimum or the maximum is, they're not telling the truth. You can poke a hole in that so easily. Yes, you can say, okay, if you graph those points really quickly, you could say that's 3, 4, 5, 6, 7. It goes something like 20, 17, 12, 16, back up to 20. I mean, it looks at first glance, that is the lowest point. 12 is the lowest point, Mr. Sindel. But what if the function did something wacky? I don't know. I can go through every single one of those points and have a minimum that's negative. You have to play devil's advocate here. It's not necessarily true. It has to be a must be true. Let's read number 2. As long as I'm between 3 and 7, f prime of c. Okay, I'm differentiable, so I can use mean value theorem. Okay, I need to actually calculate mean value theorem and see what's going on here. So mean value theorem states that the slope at a single point is equal to the slope at 2 points. So what 2 points are we using? Well, 3 and 7, I guess. Sorry, this 3 and this 7. So I'm going to say f of 7 minus f of 3 all over 7 minus 3. Okay, so f of 7. So f of 7 comes here to 20. So I'm going to say this is going to be 20 minus, okay, f of 3. F of 3 is also 20 all over 4, and that's equal to 0 over 4. And last time I checked, that's still 0. This is indeed true. And this is just one of those shortcuts that you should look for. If this height and this height are the same height, that means you can have this average rate of change be this flat line of 0, a slope of 0. This is true. Let's go ahead and circle that one. And then let's talk about 3. f prime of x. Oh, this is talking about slopes. So slope, oh, look at this. We're not between 3 and 7 anymore. We're between 5 and 7. So between 5 and 7. Talking about these points right here. If I'm connecting this point to this point to this point, it's saying that the slope at all points is positive. Well, I mean, look. It goes from here. That's a positive slope. Goes to here. Positive slope. Seems like it might be true, right? Well, no, again, play devil's advocate. Whoop, look, I'm negative. I have a slope that's instantaneous rate of change is negative there. Playing devil's advocate means that this one isn't necessarily true. Whenever you have the slope at all points, it's generally speaking not true. We can guarantee the slope at we can guarantee the slope of a single instantaneous rate of change, but not all instantaneous rates of change. So this one is 2 only. B. All right, number 3. Underlining those key words, we have continuous, we have differentiable, we have these symbols, which mean close. Underline that symbol, close. We've unlocked all 3 theorems, and we have a bunch of information going on here. We have the x coordinate of -2 has a height of -5, the x coordinate of 1 has a height of 4. Oh my goodness, and they're trying to find a false statement, which means we're going to have 4 of these that must be true. We're trying one that could potentially be false. Let me go ahead and graph this information so I can see what's going on. So again, nothing is going to be to scale here. -2, that's 1. -2 has a height of -5, and 1 has a height of 4 up here. Okay, so you can kind of see what I'm making. I'm making my intermediate value theorem rectangle. It's a terrible rectangle. Oh my God, it's not even a rectangle. It wanted to go trapezoid, full trapezoid on me. Here we go. Okay, and I'm going to quickly grab you guys and move you down right there. Okay, so that's -5. Okay, so I have my rectangle set up. I have a feeling that I'm going to be using that. So what's going on? It says, okay, all of that, in fact, all of this stuff is exactly the same with, I mean, there's some equal to signs. Ignore this stuff. I don't care. These are the things that are different. Like, pay attention to you. Okay, so this is saying what? Is this talking about an extreme? Is it talking about a height? Is it talking about a slope? What am I talking about? It's talking about a height. It must be talking about intermediate value theorem. 0. 0 happens to be inside of the rectangle, so this one must be true. So this one has to be true, and we're looking for one that could be false, which means I eliminate A. All right, what about f prime of c is equal to 0? Okay, f prime of c, that's talking about a slope. Slope is talking about mean value theorem, and guess what? You need to calculate mean value theorem. So mean value theorem states that the instantaneous rate of change at one point is equal to the average rate of change over those 2 points. So I'm going to say f of 1 minus f of -2 all over 1 minus -2. That's going to turn into f of 1 is 4. Again, I'm just reading f of 1 is 4, right? And f of -2 is -5, so minus my -5. Be careful of the double negative. And 1 minus -2, double negative. I'll just leave the double negative for now. All right, this is going to be 9 on the top, 3 on the bottom. This is going to evaluate to 3, which means f prime of 3 has to be equal to 3, or f prime of c has to be equal to 3. Doesn't have to be equal to 0. So we found the answer. This one could be false. This one has to be true by mean value theorem, which means probably C and E are also true and therefore not the answers. I think the answer is C. Let's go ahead and check I think the answer is B. Let's check C and E. What is C saying? C is saying the height is 3. We'll check it out. Height of 3 happens right there, which is inside the intermediate value theorem rectangle. Therefore, this one has to be true, and therefore that's not the answer. This one is not the answer as well because that one has to be true. And what is E saying? This thing. The height at some point is greater than or equal to the height at all points. That is the definition of a maximum. So this is saying, hey, there is a maximum. Well, that's guaranteed by extreme value theorem. This one has to be true. Therefore, the correct answer is indeed B. All right, moving on to number 4. All right, underlining keywords. We have the word continuous and differentiable. Okay, even if we had the word differentiable, we wouldn't even need the word continuous. And then we have the word closed. We have unlocked all 3 theorems. And we've got a table. Tables can be tricky. Let's find out what's going on. Which of the following statements must be true? I'm going to underline that because sometimes they try to go backwards on us and say which one must be false. All right, so it says, hey, the minimum value is a number. I don't even care what the number is. If it ever claims to know what the minimum or the maximum is, especially from a table, They're dead wrong. Those ones are automatically wrong. Again, you can play devil's advocate and say, well, I don't know. What if there's a 0.5 here that has negative 100? You don't know. You don't know that the minimum is 2. And same thing for devil's advocate on a maximum. Oh, you think the maximum is 4? Oh, guess what? 1.5 has a height of 100. You can plug in anything that you want in a table. You have incomplete information with a table. All right, what about C? C is saying the height at all points is positive. Well, I mean, these heights seem to be positive. And then again, play devil's advocate. Well, did you know, Mr. Sandell, that 2.5 had a height of negative 100? Again, playing devil's advocate might make this not true. This is saying the slope at all points is negative if we're only talking about between 2 and 4. I mean, and if I'm talking about these points between 2 and 4, it seems to be going down, going down, going down. Usually when we're decreasing, the slopes are negative. But again, play devil's advocate. What if 2.5 had a height of 5? 4 to 5 means I have a positive slope. This might not necessarily be true. All right, what about E? There is some f prime c where it is equal to 0. That sounds suspiciously like mean value theorem, but I won't know that until I actually do mean value theorem. And if you remember the shortcut from before, you might recognize, oh, these two heights are the same. That sounds vaguely familiar. Mean value theorem is saying that the f prime of c, the slope at 1 point is equal to the slope at 2 points. You can say the slope from 4 to 0, so f of 0, all over 4 minus 0. And that's 2 minus 2 all over 4, which is 0 over 4, which is indeed 0. And this is true, and it has to be true by mean value theorem. Moving on to number 5. All right, we've got a function that is differentiable, therefore it's also continuous. Oh, it's open, so it's not closed. Interesting. Which of the following must be true? So we only have mean value theorem. We don't have extreme value theorem because it's open, it's not closed. So what's going on here? Mean value theorem. We have horizontal tangents. What does that even mean to be a horizontal tangent? That's a really important term to define. A horizontal tangent is if I have some sort of graph, I have a tangent line that is horizontal, meaning I have some sort of f prime of, let's go ahead and say that's like c. Let's say that that x coordinate down here is c. That f prime c is equal to 0. It means that if I take its derivative, I have 0. This is talking about mean value theorem. So this is the one that I'm suspicious of. So I'm going to definitely be checking you. This is talking about a height, and this is talking also about a height. Height is equal to 3. Height is equal to 0. And then it's saying that there's 2 of those that are equal to 0. Interesting. So I have to be careful here. Nothing in here was talking about an extreme. Extreme value theorem needed this to be closed. This is not closed, so we can't verify that there's mins and maxes. But none of these were talking about mins and maxes. So what I'm going to do is I'm going to erase all of this stuff. And I'm going to graph what's going on because we can still use intermediate value theorem, which means we still need to see what's going on here. So intermediate value theorem, we have 2 here, we have 5 here, we have 9 here. When I go to 2, I go down here to a height of -5. When I go up to 5, I go up to a height of 5. And when I go to 9, I go down to a height of -5. So this is the information that's being given to us. 2 goes to -5, 5 goes to 5, 9 goes to -5. What's going on? So really, I have 2 different types of intermediate value theorem. I have an intermediate value theorem rectangle right there. And I have another intermediate value theorem rectangle right here. So I have 2 different rectangles. Let's talk about this one. I have at least 2 zeros. I have a height of 0. So be careful. This is really talking about a height. And I do have a height of 0 because 0 is inside of this rectangle and 0 is inside of that rectangle. There are 2 of those zeros. So this one is definitely true. So let's go ahead and circle that one. That one is true. What about number 2? The graph of f has at least 1 horizontal tangent. 1 horizontal tangent means I have 1 slope that's equal to 0. And check it out. If I talked about that shortcut before, I'm talking about it again. This height and this height are the same height. If I connect those 2 with a line, that is a horizontal line, and that horizontal line has a slope of 0. Therefore, it is a slope of 0 for our mean value theorem. Again, you can verify this algebraically by saying, okay, f prime of c The slope at one point is equal to the slope between 2 points, f of b minus f of a all over b minus a. In this case, this is going to be equal to f of 5 minus f of, no, not f of 5, f of 9, I apologize, because 9 was the end interval, right? F of 9 minus f of 2 all over 9 minus 2, and that's going to be -5 minus a -5 all over 7 is going to be 0 over 7, which is equal to 0. And when f prime is equal to 0, that's a horizontal tangent. So that's kind of an important definition you need to know. Whenever you see the word horizontal tangent, immediately in your mind, switch that out for the word f prime of c is equal to 0. And that is indeed true. F prime of c is equal to 0, so this one is also true. No question about it. Last, and maybe least, we'll see, f of c is equal to 3, between 2 and 5. So between 2 and 5, I'm talking about this rectangle right here. Is the height 3? Well, 3 is right here, which is inside the rectangle, so this one is also true. All three of these are true. The correct answer is E. I think I might have misspoke at the very beginning and said only mean value theorem is true, but intermediate value theorem is also true because if it's differentiable, it's continuous. And intermediate value theorem only needs to be continuous. Whew, all right. And now, oh, we're not even on the last problem. We got 2 more. Number 6. All right, underlining our keywords. We got continuous, we got closed, we got differentiable. All 3 theorems are unlocked. There we go. There's the word I'm looking for. Which the following could be false, which means 4 of these have to be true. All right. The slope at one point is equal to the slope between 2 points. That's literally mean value theorem. This one cannot be the answer because this one has to be true. We're looking for one that could be false. This one has to be true. That's literally mean value theorem. All right, what about B? It's saying that the slope at one point is equal to 0. Well, again, it's suspicious. Like, we can use mean value theorem, but it didn't give us any information where we could plug in values. So this one is probably the answer, because we don't have enough information to say, hey, the slope is a certain number. Let's talk about C. There is a minimum. That's literally extreme value theorem. This one is true by extreme value theorem. This one is true. This is mean value theorem. This is just another true by extreme value theorem. It's the other side of it, right? Extreme value theorem guarantees there's a minimum. It guarantees there's a maximum. Those have to be true. Therefore, it's impossible for them to be false. What the heck is this thing even saying? What is this S symbol? It's an integral symbol, but you guys don't even know what that's talking about, and that's okay because hopefully you saw that B was false. Sorry, the E does come from Unit 5. We're not ready for that yet, so it's not E. This one has to be true. You can always take the antiderivative whenever the function is differentiable. Well, it says it's not antidifferentiable. That's a harder question. I'll talk about that later. We can come back to that in Unit 5. Number 7. The function is continuous. Okay, underline that keyword continuous. And we have a closed interval. Do we have, and again, is there a word differentiable? Differentiable, I'm looking for you. I don't see any word that says differentiable, which means you cannot use mean value theorem. Look for something that's talking about f prime. Uh-oh. But these are all talking about f prime, Mr. Siddell. What's going on here? F prime of c is equal to 0. Oh, this is interesting. So it told us that there's a horizontal tangent, that f prime of c is equal to 0. This is impossible. Wait, so there is no c where f prime of c is equal to 0. Which of the following statements must be true? Okay. Let's go ahead and make a picture of what's going on here. I think that'll help us with this case. So f of -2 and f of 2 are equal to 0. So I have a graph that says when I go to -2 and when I go to +2, I have something happening where they're the same, they're on the x-axis. So sorry, they're equal to 0. That height is equal to 0. That height is equal to 0. There's my picture of what's going on. And it's saying, but there's this weird thing happening where no matter what happens, I will never, ever, ever have an instantaneous rate of change equal to 0. So you cannot have any sort of flat line. I can't just connect them with a flat line. How can you connect this point to this point? It is continuous, so you have to hold down your pencil. Without picking up your pencil, how can you connect these two without doing a flat line? And you guys have seen this before, but here you go. Look, I never picked up my pencil between those 2 points, and I never made a horizontal tangent. What did I do? I committed the sin of being not differentiable. I had a sharp corner. So how do you somehow say there's a sharp corner? That's what I'm really looking for. I assume in here. This is saying, oh, well, so K is some point. The slope at some point must be positive. Maybe. The slope at some point must be negative. Possibly. The slope at some point exists. Well, that point didn't exist. The slope exists, but it's not continuous. It said it was continuous, right? This is literally the opposite of what it says in the instructions. That this is the dumbest thing I've ever seen. All right. And this is the thing that I'm looking for. F prime of K does not exist. There's a slope that does not exist. There's a slope that makes it, what's the word I'm looking for? Non-differentiable. This is the same thing as saying it's non-differentiable at some point. And that is exactly what we're looking for. It is indeed E. And I'm trying to find a way to disprove A and B because it felt like, yeah, you can have a negative slope. You can have a positive slope. While picking up the pencil, I'm trying to figure out a way. Can I make it so that, yes, here, I found a way to disprove it. What if I had a graph and I'm trying to connect this point to this point? I can make it so that the slope is always negative, disproving this one. You guys want to see it? Ready, set. Slope is always negative, and then I have a horizontal tangent. I guess you can argue like, well, if it's curved down there. Okay, here, I'm going to make it not curved. It's going to come down here, and then it's going to be a straight line up, and then I connected them. This slope is infinite. This slope is negative. None of those slopes are just simply positive. And you can do the same type of slope over here. You can say, if I'm trying to connect these 2 points without ever making a negative, only positive, you connect like this and then come straight down. So I can disprove those two with those two graphs. This is saying the slope or the slope somewhere exists, which, oh, sure, the slope can exist there. This is really the one that you're looking for because there's a slope that doesn't exist. There's some sort of sharp corner. Whew, those were some tricky problems, guys, but that does conclude our worksheet 1-9 for intermediate value theorem, extreme value theorem, and mean value theorem AP problems. Thanks for watching.